this indifference curve. And what am I consuming there? Now all of a sudden I'm consuming a lot of water, but I'm consuming some champagne. Right? So what these quasi-linear indifference curves have, they have this cool property right here that if prices are relatively steep, meaning one good's relatively expensive compared to the other, you can be at a corner solution, but if the expensive good becomes cheaper, you shift from this little corner solution point potentially to an interior solution point right here. Right? So if we drew the old budget constraint from the last problem right here, right, our answer for the last set of prices would still be the same as before. So under the old budget constraint where the good was really expensive, we would still consume at the corner where I6 is the highest indifference curve we can get on. But because the budget constraint now changes, our opportunity set is much, much bigger because champagne has become so much cheaper and income is the same. We now basically rotate our budget constraint out, and it now includes this little wedge of an opportunity set before that we didn't have before, which gets us on a higher indifference curve. So we go from a corner solution to an interior solution. Yes? No, if I want you to draw quasi-linear, I'm going to tell you I want quasi-linear preferences, right? But I'm not going to ask you for quasi-linear preferences on the exam because you guys don't want to grade that question, okay? We've done it in the past, and the students who overstudy for this one, they get it, but of those students, there's usually 5 in a class of 160. This is a hard question. The reason I make you go through this is I want to show you that this relatively simple model really accounts for a variety of settings, right? We need to be able to account for things we'll only ever consume 0 of, or positive quantities of. We need to be able to account for things where, depending on the prices, relative prices, you consume 0, or an interior solution, positive quantities, or both, or there's certain goods where we'll always consume positive quantities of both, right? So this model is flexible enough, and the prediction depends fundamentally on your preferences. And who determines your preferences? You do, right? They're your own. Nobody can take your preferences from you, even though if any of you watched that foosball game on Sunday, they tried really hard, right? What do they try and do? They sell you stuff, right? What's the point of advertising? It's the point there is to change your preferences, right? You didn't know that you needed, I don't even know. I watched it online. There were no ads. It was awesome. But you didn't know you needed whatever it is they were putting out this year, beer with, a couple of years ago it was lime flavor. I don't know what we're doing now, tangerine flavored beer. They come up with ways to help change your preferences in their favor. That's the point of advertising. But we can talk about that later. Okay. Now what you saw here, what I sort of snuck by you is I changed the price, and the budget constraint did, whoa, it rotated out, right? Let's look at this a little bit more carefully because this is really the fundamental move we're going to look at in order to derive the demand curve today. Today, we're going to get to demand. It's pretty amazing. Okay. So let's move the budget constraint around a little bit for a second, or what makes the budget constraint move? There are two things that make the budget constraint move. The first thing that makes the budget constraint move is if a price changes. Either the price of Reese's or the price of Hershey's changes. That moves your budget constraint in a certain way. The second thing that makes your budget constraint move is if your income changes, right? So either one of the prices or both prices change or income changes. So let's look at what happens if a price changes. Here I'm going to look at the increase in the price of Hershey's for a second. So assume that income is $8, price of Reese's is $1, price of Hershey's is another $1. All right. So again, we're going to stick with our convention that Reese's are on the x-axis. Reese's are on the y-axis. Hershey's are on the x-axis. Slow down, Max. So let's do that. Let's draw our budget constraint. If I spend all my money under these prices on Reese's, 8 divided by 1, I can afford to buy 8 units of Reese's. If I spend all my money on Hershey's, $8 of income costs $1 a unit. Again, you can do 8 units total. So my budget constraint is this here. Includes things like 4, right? 4 each. So that's the budget constraint under these prices. Now what happens? There's our crisis in Pennsylvania that's unrelated to fracking, right? There's a chocolate crisis, and I don't know, some exogenous rainfall shock happened, cocoa prices explode. It somehow doesn't affect Reese's because they bought forward contracts. Does affect Hershey's, right? And your price of Hershey's, I'm just kidding. The only thing that really matters here is that the price of Hershey's goes up. But so price of Hershey's goes up, price of Reese's stays the same. So how many Reese's can you buy? Price of Reese's is the same. 8, right? Stop asking dumb questions, Max. 8, right? The price didn't change, income didn't change. How many units of Hershey's can you buy now? 4, right? Draw the straight line between the two. Your budget set just shrank. Right? The budget constraint rotates in. Right? It doesn't shift parallel, but it actually does a rotation, right? Around the price that didn't change. What does that mean? Does your marginal rate of transformation change? What's the marginal rate of transformation again? It's the slope of the budget constraint. It's the ratio of prices, or relative prices. So here before, right, MRT is equal to -1. Right? If you forget how to write it, just go back to your formula. Here we go. So it's always pH over PR, because we always have Reese's on the y-axis, right? So pH is now 2, PR is 1, so the marginal rate of transformation is now -2. It just means how many Reese's do you have to give up to get one more Hershey's, right? In order to buy one more bag of Hershey's, you're going to have to pay $2. So you somehow need to free up $2 worth of Reese's, and $2 worth of Reese's are 2 bags, right? So -2. So the marginal rate of transformation, or the slope of the budget constraint, changes if the price of one of the goods goes up. All right, let's do one more. All right, I didn't do this last year, but you guys are sharp, I can tell. Let's do the following. Let's say, yes. Can I take 2 slides to get to that point? So you're already in the future, but I don't want you thinking that far yet, right? So you're already putting indifference curves on these new budget constraints and thinking about what happens at the optimum. I'm gonna walk you through that, okay? And the answer is whatever indifference curve is going to be tangent to this line here is going to have a different marginal rate of substitution at the optimum than at this point here, right? But I'll walk you through that slowly. Let's do one more thing here. Let's go crazy and pull out a third color. Why? Because I can. Here we go, green. Now, some guy at Reese's figured out, holy cow, I bought a forward contract on cows, not cocoa beans, all right? So the price of Reese's all of a sudden also goes to $2, right? So now the price of Hershey's is $2, but the price of Reese's also goes to $2. So if you buy Hershey's with your $8, you can afford 4. How many Reese's can you afford now? 4, right? So the budget constraint now, if income stays the same and both prices double, is the green one. What's the marginal rate of transformation of that budget constraint? Oh, you guys make me happy. All right, at least the ones of you who yelled the right answer. the marginal rate of transformation here again is -1, right? It's the relative prices. How many Reese's do you have to give up to get one more Hershey's? Well, in order to buy one more Hershey's, you need $2, so you need to give up $2 worth of Reese's. Since the price of Reese's now is $2, it's exactly 1. So if prices of both goods double, your marginal rate of transformation remains unchanged, right? Because the marginal rate of transformation is simply the price of one good over the price of the other good. If you multiply both by 2, the 2 cancels out, and your marginal rate of transformation remains unchanged, all right? That's interesting, Max. Why are you doing this? Let me show you, all right? The reason I'm doing this, let's look at an income increase, all right? Let's say you have $4, Y is 4, and the price is here. Price of Reese's is 1. Price of Hershey's is also 1. So if you spend all your money on Reese's, you have $4. This is not written out nicely. $4 divided by the price of Reese's is 1. So you can afford 4 Reese's. You have $4 divided by the price of Hershey's, which is also $1. You can afford 4 units. So your budget constraint looks something like this. Now, grandma. We love our grandmas, right? Because grandma will forgive you anything. She'll think you're the greatest thing since sliced bread. And most importantly, she sometimes sends you $20 in the mail when you most need it. I don't know how they figure it out, but for some reason, right when you thought you couldn't go out on a Friday night, $20 arrived from grandma. Isn't that true? I don't know. Maybe they just know that on Friday you run out of money. But the point here is, what I'm going to do now is I'm going to draw you a budget constraint, and I'm going to ask you how much money grandma sent you. How much money did grandma send you? $4, right? Your new income now is twice what it was before. How did you figure it out? Price of Reese's and price of Hershey's is $1. You now can afford 8 of each, so your income is 8, right? So grandma sends $4, so income is 8. Okay. So if your income doubles, the budget constraint shifts out parallel, right? The marginal rate of transformation here is the same because prices didn't change. Now, do you see these two budget constraints somewhere else on this graph? They look similar, right? This red one right here is exactly the post-grandma budget constraint. The green one here looks exactly like the pre-grandma budget constraint. Turns out, the doubling of prices has the exact same impact on your budget as a halving of income. Or the doubling of income has the same impact on your budget constraint as a halving of prices, right? So whether you have inflation of 100%, right, meaning prices double by 100%, or your income doubles, it doesn't matter. It's the same thing here, right? So the important point I want to take away here is the following. If your income goes up, your budget constraint shifts out parallel. If your income goes down, your budget constraint shifts in parallel. Your marginal rate of transformation is unaffected. If the price of one good rises, and we'll usually let the price of the good on the x-axis rise, your budget constraint rotates in, and your marginal rate of transformation changes. If the price of the good on the x-axis drops, your budget constraint rotates out, and your marginal rate of transformation changes as well. If both prices increase in the same percentage fashion, easiest way to think about it is if prices double, your budget constraint shifts in parallel, and your marginal rate of transformation stays unchanged. So if all prices increase by the same proportion, that's equivalent to an income decrease by that proportion. All right? So what I want you to do when you get home is, have some Arrowhead water, or tap. Actually, you should drink tap water, but that's a different class. What I want you to do is just, this seems totally obvious to you right now, and seems like something you learned in pre-K. When you're asked to do this on the exam, you're going to start freaking out about it. Okay? So just make sure you can redraw what I drew here and make sure it seems intuitive. It seems intuitive to you now, but trust me, later it doesn't. Okay. Here we are. This is a big moment. All right? What's Max been doing? Max has been boring us to tears with bad jokes, bad fashion, and fast speaking. But what I'm going to do now is I'm going to show you how everything we've done so far gets to the economic concept that said grandma knows, right? Which concept does everybody know? Nobody understands it. But when I sit in the airplane and somebody asks me what do you do, and I say I'm an economist, the first thing they want to do is ask stock market tips. I've got nothing to add there because that's finance, right? Different. And then they say, oh yeah, supply and demand. I understand that. Everybody knows supply and demand, and then you ask them to label it, and they're confused which one's supply and which one's demand. But what all economists agree is supply and demand is an incredibly powerful model because we can shift around demand curves and supply curves and come up with interesting predictions of what different types of policies do. But understanding where demand actually comes from is actually, if you ask people, they have no idea. It's a curve, right, that economists use. It comes out of nowhere. Well, actually, demand comes from two things. It comes from a budget constraint or a set of budget constraints and your indifference curves, right? So I, Maximilian Aufhammer, can derive a demand curve for you for a given good if I only knew your indifference curves, right? So I'm going to assume that I know your indifference curves. That's actually a questionable assumption. I'm going to assume that I know my own indifference curves, and I'm going to show you what my demand for, which one are we doing? Hershey's looks like, and how to get to it from the simple concept of indifference curves and budget constraints. Let's go. I'm excited. All right. Let me make sure my pen has the right color here. Yep, red. We're ready. You go over here. Whew. Reese's. Check. Hershey's. Check. Okay, here's some parameters. $20 in income. Reese's will always be $2. All right. Throughout this example, you're going to have $20. I'm not going to mess with that. And I'm going to let Reese's cost $2. I'm also not going to mess with that. So that's going to be the same throughout. So if I have $20, Reese's cost $2, I can afford 10 bags of Reese's. Awesome. All right. Now I'm going to assume that the price of Hershey's is $10. If I have $20 total and I want to buy all Hershey's, I can afford 2 bags. Here's your first budget constraint. I'm a little nervous. This is exciting. Okay. Here's my first budget constraint. Well, on that particular budget constraint, I'm going to find my optimal consumption bundle in a minute, assuming I'm on the budget constraint, but I want to draw a different budget constraint and a different one after that. So I'm going to have to be really tidy here. So what I would suggest is for a second, put your pen down, watch me draw this, right? Because there's a lot of drawing going on, and then we can go back and draw it again, or you can watch the stuff online and see it drawn again. But pay attention to this one, because getting the ultimate picture right is easy, but how we got there really matters here. All right, so this is my first budget constraint. I'm going to find the indifference curve, which is going to be blue, if this thing will let me. Thank you. That is tangent to that particular budget constraint, okay? I'm going to argue it looks, why am I going to erase this? That's upward sloping there. Is that illegal? Yes. All right. Upward sloping indifference curve is very illegal. Oh, this is really painful. Okay. Here we go. Let's try this again. I'm sorry. Somebody's Siri's talking. Here we go. Budget constraint. Now let's draw the indifference curve. Okay, I want this thing to be tangent here. Yikes. Why did you cut out on me in the most important parts? Here we go. Okay, that's an indifference curve. It's a little shaky. You can tell I'm a little bit nervous, right? Or maybe I can make this bigger and draw this way. That'll make it easier. Okay, so this is that top right graph right here. This is my difference curve. My tangency here, the optimal consumption bundle I can get on this budget constraint given these prices is going to be this dot right here. Okay, now I'm going to let the price of Hershey's go down to $5. If I spend my $20 on Hershey's now, I can assume 4. Price of Reese's didn't change, so budget constraint rotates out, and we get a new budget constraint. And this is what Lars wants to get to sometimes. Maybe shaking is suboptimal. Oh, this is, where are we? Okay, I'm going to go super quick drawing here. It was 10-2, right, was the first one. Let me draw you all 3 budget constraints, okay? The second one is now Hershey's is $5, so I can do 10-4. And the third budget constraint, now the price of Hershey's is 2, so it's 10-10. I'm going to have to make sure I get there. 10-10. So 3 sequential price drops, right? So budget constraint 1, actually I don't want to put that right there. So this here is budget constraint 1 with a high price of Hershey's. This one is the $5 price of Hershey's, and this one right here is the $2 price of Hershey's. Now I'm going to draw the indifference curves for my preferences that only I know for each of these budget constraints. And this is a little bit tricky to draw. So I'm going to draw where I want my tangencies, and then I'm going to draw indifference curves that go along with that. So 1. Come on, Max, you rookie. Oh. Okay, I owe you guys some chocolate. I'll bring some chocolate in next time, because this is... What? On the wrong slide? I'm just zoomed in. No, I'm on the right slide. Oh, no, you're right. Oy. Take a point off my teaching evaluations already, okay? Some of you, not all of you. That would be detrimental. I'm trying to be so good here, and technology is not letting... Well, let's blame user error. Okay. If we draw it 5 times, maybe we'll learn it better. Budget constraint number 1. So that's for the price of 10. Price of 5. You have $20, so we go to 4. And then 10-10. If this screws up again, I'm going to the blackboard, which will work. Okay. Now, sorry? I will do. Reese's, Hershey's. Okay. So let me pick out some possible points of tangency here that are consistent with what I know my indifference curves to be. Here's indifference curve 1. Here's indifference curve 2. And here is indifference curve 3. So the way I'm doing it, I'm not supposed to pick this point. I'm supposed to draw my indifference curves and then put these points there, which are the points of tangency. But sometimes it's just easier to figure out where you want your tangencies to be so you have enough room to fit the indifference curves through for the picture you want. So I sometimes just pick where I want them to land, and then I draw the indifference curves. But if your indifference curves are a little bit rotated, your points of tangency could be here, here, and here. It just depends on the indifference curves you have. But I just have, for my preferences, these points in mind. But it could be anywhere, and actually we'll play with that quite a bit. All right, so what do we have now? Let's look at our nice, beautiful graph here. What I have here is I have 3 budget constraints. The one closest to the origin is the one where Hershey's are really expensive. They're $10 a bag. The second one is where Hershey's are $5 a bag, so pH 2 here. And the third one is where Hershey's are relatively cheap at $2 a bag. What I have is for each of these prices, I now know what my optimal consumption bundle is, right? When Hershey's are really expensive, I'm consuming this bundle. When Hershey's are $5, I'm consuming this bundle. And when Hershey's are $2, I'm consuming this bundle. So how many Hershey's do I consume in each of these? I can just go down to my x-axis here and read off how many Hershey's I'm consuming, right? So if we zoom in a little bit here, when Hershey's are expensive, I'm consuming about 1.2 bags of Hershey's per day. When Hershey's are $5, I'm consuming about 2.3 bags of Hershey's per day. When Hershey's are much cheaper, $2 a bag, I'm consuming about 3.8 bags of Hershey's a day. And I'm coming up with these decimals roughly where these lines land. So what this picture here contains is the optimal number of Hershey's consumed at 3 different price levels, right? This is 1.2 Hershey's at a price of $10 a bag, 2.2 Hershey's at a price of $5 a bag, 3.8 Hershey's at a price of $2 per bag. Now, so this picture of indifference curves right here and budget constraints shows me everything I need to know about my quantity consumed or quantity demanded at different price levels. Well, if you go back to your Econ 1 knowledge that you've all retained, of course, demand tells me the optimal quantity demanded, right, at different price levels. So this picture right here tells me the optimal quantity demanded for Max at different prices of Hershey's. Now this looks nothing like a demand curve, right? What's on the axes of this graph here, thanks to one of you? Reese's and Hershey's, right? This space here